So thanks for coming to the second day of the workshop. Yesterday we covered the TensorFlow portion. We'll get back to TensorFlow and some implementation details tomorrow. But first I wanted to spend some time going over what neural networks actually are and why we care about them. In case you weren't able to make it to yesterday's talk, I know there are some seminars going on at the same time. I've uploaded some preliminary videos of the two talks from yesterday along with the slides. And I'll upload improved or higher quality videos as I compile them. But these are just the raw footage from yesterday's talks. And you can find this on my math department website, which is at math.purdue.edu, and my name is Nick Winovich, and I'll post a link or send out an email later today with the exact link to the website. So as I mentioned today, I want to start going over neural networks and the underlying theory behind these networks, as well as talk about why we should care about these neural networks or why we should expect them to work. So to begin, just the basic idea behind an artificial neural network, or just a neural network. We envision these as computing systems which are composed of basically a network of computational blocks. In particular, we try to leverage the connections or the connectivity between these computational blocks to execute highly complex computations in small, manageable bytes. And so two references that I think are good to get started with neural networks are provided by Goodfellow, Bengio, and Corville, their deep learning book, which is available in print on Amazon as well as online for free at deeplearningbook.org. And then also some of the video lectures from Stanford, and in particular CS231N. So these are two good references to get started with, and I would highly recommend consulting those if you want to go into more detail after today's talk. So if we can just jump right in, what is an artificial neuron? These are the building blocks of neural networks. And as we can see in this diagram, there are three main components of artificial neurons. One, there are weights, which are used to scale the inputs. Two, there are bias terms, which are used to shift or act as a threshold in each unit. And lastly, there is an activation function, which provides a nonlinear processing aspect to the neuron. The way that we interpret the previous diagram is that the output y is produced in the following manner. So we take the inputs x, we multiply them by the weights w, add that together, and in addition add a bias term. Once that is computed, we apply the activation function labeled f. And if we take a minute just to look at this, it's pretty easy to see that this is actually just a inner product between w transpose and x. So we can write this in vector form as y is equal to f w transpose dot x plus b. And this will be helpful because when we're trying to implement these on computers, we want to form, as much as possible, the systems as a linear system so that we can take advantage of linear algebra computations and optimization algorithms. So what if we have a situation where we need to predict two values, not just one, or more generally, any number of values? Well, we can take those same inputs, x, 1, 2, and 3, so the same inputs are provided, but we'll instead use two neurons in this case. So we'll have separate weights, these W1 weights for the first neuron, and these W2 weights for the second neuron, and add distinct bias terms or thresholds for each of them, and typically apply the same activation function. So we can write this as a pair of equations, y1 and y2, just copy the equation from the previous example, or we can organize this as a matrix equation. So if we stack W1 transpose and W2 transpose into a matrix, this is simply y, the system y, where y is y1 over y2, and that's equal to f w dot x plus b, where now we have a matrix vector product. And we assume that the vector in this case has been vectorized or acts element-wise, and hopefully we have an implementation like in TensorFlow or NumPy, which takes advantage of ways to efficiently compute this on arrays of numbers. So this leads to the concept of what's referred to as a fully connected layer. And the diagram here is a more common or typical example of how we would represent the two-neuron or the two-output example that we just covered. So we take those inputs, x1, x2, and x3, we assign them to basically nodes. They fill those nodes, and the edges refer to the weights of the network. So the weights connect each node in the graph, and they connect it fully in the sense that every node from the input layer is connected to every node in the output layer. So this is referred to as a dense or fully connected neural network. Now, when we're trying to implement this numerically, we want to keep track of the floating point operations and how the computational complexity of implementing this. So if we take a look at the matrix vector product, it's relatively simple, but just to get a sense of how we compute these, we go through one by one. Here I've broken it up into the multiplication steps and the addition steps. So if we take the input vector x1 to xn, we have our rows of the weights from each output, and we take a matrix vector product. What we'll do is we'll lay this down, multiply each element. So x1 to xn will be multiplied by each row, and then we'll sum those values up. And if we count this, we get m times n multiplies and m times n minus 1 additions, where the n minus 1 corresponds to adding n terms together. We only need n minus 1 addition operations. So we see the total count, if we ignore the biases, for the linear aspect of this is 2mn minus m. And then if we go ahead and take into account the bias terms, which there will be one bias term for each output, m, we'll get the rounded 2m times n flops. Okay, so this is a typical example of how we compute the flops for a single dense network layer. One thing to note, however, is that this is disregarding the computation required for the activation function. So this is just the linear aspect. And if we have a highly nonlinear activation function, that can play even more significant role. So we do want to choose the function that we use for the nonlinear aspect of the neuron carefully. So the activation functions, as I mentioned, are responsible for all of the nonlinear aspects of the network. If we just composed a series of these neurons without activation functions, it would still just be a linear operation. Okay, so it would be a waste to make a string of them. So instead, we want to add some type of nonlinearity, but we want that nonlinearity to be efficient to implement. So in practice, one of the kind of most basic nonlinear functions, in some sense, is used and often works perfectly well. And that most basic quote-unquote function is the rectified linear unit. Okay? And so this unit is piecewise linear. It simply takes the value 0 for negative values and x for positive values. Okay, so it has slope 0 and slope 1. So when we're backpropagating or computing gradients, we get a derivative of 0 or 1. So it is a very simple derivative, very simple to compute the value of the function as well. And so this is a very computationally efficient choice of an activation function. Okay, we'll need to string some of these together, most likely, to get complex nonlinear functions out of our networks. But for many applications, this is sufficient. So an approximation, and there exist many of these, an approximation to the rectified linear unit, which is smooth and may have some advantages in terms of propagating derivatives back. It also doesn't ever have a 0 gradient, which can also be helpful, is the soft plus activation. And we see it's somewhat of a smooth approximation, which levels off for negative values and approaches the line y equals x asymptotically. In other cases, we may want our nonlinear functions to be bounded or to lie in some interval. And two convenient activation functions for this case are the sigmoid function, which restricts its outputs to the interval 0 and 1, or the hyperbolic tangent function, which takes values between -1 and 1. And so these were some of the classical units that were used back in the 90s. They were very prevalent. Now, more commonly, things like the ReLU or variants of the ReLU are starting to be used. In particular, we can imagine the following two parameterized activations. So we're going to have a hyperparameter which we select, and we want it to be able to approximate a rectified linear unit, but possibly add some more flexibility, and also avoid having a completely zero gradient, because this will basically allow neurons to die. If the gradient is 0, the optimization algorithm will never care or think to adjust that value. It will be stuck at the 0 gradient of the rectified linear. So in contrast to that, we can define the exponential linear unit, which is linear to the right and exponential to the left. So it has something of an exponential leveling off, but still is not quite 0. Or we can just slightly bend the tail, the negative tail of the rectified linear unit, which is referred to as a leaky ReLU. And this is defined, again, with a hyperparameter corresponding to the slope on the negative end. And lastly, just another variant or class of activation functions, we have activations with learnable parameters. So the previous two activation functions had hyperparameters, which we would specify. In some cases, it's helpful to have the network learn what activation function is best. And in this case, we can see these parameters beta adjust the activation function and are modified by the optimization procedure to obtain the best performance, hopefully. So the parameterized rectified linear unit is similar to the leaky ReLU, except it will have a constant slope of 1 for the negative values, and then the adjustable component is for the positive values. And the swish units are defined and somewhat unique among these in the sense that they have a decreasing component as well. But they are approximations to either lines or rectified linear units, depending on the value of beta. So if we take beta to be close to infinity, what we get is approximately just a straight line. And if it's close to, or what we get is approximately a rectified linear unit. And if we take beta equal to 0, for instance, we get approximately x over 2. So as beta grows to infinity, we actually get a cutoff between negative and positive values. OK, so that's the basic essence of neurons. Those are the building blocks, and there's not a lot more to say about the neurons themselves. They just consist of basically a matrix multiplication, a bias shift, and an activation function. Where things become more interesting, and we start to leverage, again, that idea of connectivity, is when we introduce hidden layers. So these hidden layers are just intermediate network layers between our inputs and our outputs. And if we think back to the definition of a single network layer, we remember we defined our outputs in terms of f of wx plus b. So we can first define some layer called h, a hidden layer, and then apply the same process again. So in terms of our equations, we can just define y in terms of this intermediate layer h. And this is visualized in the diagram on this slide by providing nodes in between, as we may expect, the inputs x and the output y. And so this is something of a typical example of a fully connected layer, and we can imagine obviously adding more hidden layers in between to get something of a highly nonlinear or more nonlinear function. And again, the equations for this are straightforward. We just have h1 defined in terms of x, h2 defined in terms of h1, and y defined in terms of h2. So it's very simple to construct this. The difficulty, as we'll see, comes in tuning or identifying how the parameters x, h, h1, and h2 affect the final output. So we need to find a way, typically in terms of gradients, to decide which direction we should adjust the network weights or biases. And to do that, we have to characterize the influence that each of those network parameters has on the final output. So we'll need to address that later. But for the moment, the forward pass, so to speak, going from your input x to your output y is relatively straightforward. OK, so we have this concept of a neural network. The natural question is, why should we think that these neural networks are worth working with or are capable of approximating a given function or solving a particular problem? And the general idea behind this came about in 1989, actually independently by a handful of researchers. In particular, the single-layer result was shown by Sybenko in 1989, and they showed that on a hypercube, or basically just a compact set, we can approximate any function, any continuous function, by a function of the form here. And if we break this down and think about this, this is actually exactly the representation of a neural network with a single hidden layer. We have the first activation function, or the activation function is applied to the linear transformation of the input values, and the results are summed. So this is referred to as a superposition of sigmoidal functions, but it can also be characterized as a neural network just with a single layer. And he showed that already with a single layer, it is possible to arbitrarily approximate, or approximate to an arbitrary degree, any continuous function. And this approximation is with respect to the so-called supremum norm. It just means that for any function that's continuous on a compact set, and any tolerance that we have, epsilon, we can always find a single-layer neural network which is close to that original function and close everywhere with respect to that tolerance. So this inequality holds for every x in that set. So this is a good start. But in practice, the deeper networks may be more realistic to train with, or more practical to train with. So we need to extend that result to multiple layered neural networks as well. And that was done in the same year independently by Hornick et al. And Funahashi. And the basic idea of their results is that for any compact set and any multi-layer feed-forward neural network, we still have the same property. It's dense. That collection of functions is dense in the set of continuous functions with respect to the supremum norm. And they had two basically criterion or list of criterion. The networks had to have activation functions which were continuous and increasing and non-constant and bounded. Okay, so relatively simple constraints, but the bounded part would eliminate the rectified linear unit, for instance, from being applicable in this situation. So we still aren't quite done with justifying the use of our current neural networks. But in 1992, Leshno et al. Basically came out with a result, a more general result that, in fact, as long as the activation functions are not polynomials and they are locally bounded, then the multi-layer feed-forward neural networks are still dense. So they're still dense in that supremum norm sense. But this does not hold without bias terms. So it's an interesting note. In practice, sometimes you can get away without using bias terms, but the theory, at least in this form, only holds with those bias terms. So something of note. So that was a very basic review. There's additional results that have come out, but that is basically the driving motivation for why we study neural networks is we have this universal approximation theorem. So they serve as a tool that we can use as our models, and they're not restricted in terms of applicability. OK, and so now, once we've defined these networks, we'll start to see immediately that you can add layers and you can add more and more neurons, but you may not actually be performing as well as you would like. And one kind of classical problem that you may run into is that of overfitting. So as we train our model on a training data set, our model may learn too much, so to speak, about that specific training set. Maybe there are some very complex relationships that completely describe and accurately describe all of the training examples, but it's too complicated, or it's not able to generalize to other examples which the model hasn't seen. So here, in kind of a cartoonish example, we see that the data is actually linear. We have a line of data. The model has only seen the blue points, and it's found this perfect solution by approximating it with a cubic polynomial, but it really misses quite poorly the validation set, or the points that it hasn't seen. And it will continue to do worse as we get further from that training set. So this, again, is a motivation for using training and validation. But once we identify that, how do we actually fix it? So there are a number of approaches. The first, and perhaps most classical, is that of weight regularization. So we can imagine enforcing some constraints on the norms, the L1 or L2 norms, of the weights in our network so that we don't have too large of a fluctuation, effectively. We don't want our inputs to be multiplied by 1,000 and then multiplied by 1,000,000, et cetera. It's likely to be overfitting or doing something that we really are not trying to learn. So by enforcing some constraint on the L1 or L2 norms, similar in the underlying idea behind like lasso or ridge regression, we can basically apply this Occam's razor principle, which is effectively saying that the simplest idea, the simplest way to solve the problem is most likely the best way. Okay, so in the previous example, we've solved the problem, so to speak, but there's a much simpler solution, and in this case, that happens to be the correct one. So we can do this by basically assessing a penalty in our loss term. We'll just add the sum of the weights of the L2 norms or the L1 norms. And the case of L2 regularization is a fairly general regularization technique. It just tries to target the largest values. So we can think if there's a weight which has a value of 10, and then all of the other weights have a value of 1, that largest weight gets scaled up when it's squared. And the other weights are less impactful. And in L1 regularization, we have a more specific form which is targeted for sparsity. So it encourages sparsity by not squaring these values. So if we have values like 0.1 and then one large value like 1, those values of 0.1 can still add up to contribute to the overall loss. And in that sense, they will be encouraged to go down until they're 0, at least in kind of the heuristic explanation of L1. Another way to correct the problem of overfitting is dropout. So dropout is a way to basically avoid having any specific nodes in your network have too much influence on the final prediction. And the way this is achieved is by randomly dropping out or removing nodes in the network during training. So what we do is at each training step, we take a random sample of Bernoulli values, either 0 or 1. If it's 1, we keep the neuron. If it's 0, we reject or remove that neuron. And then just as a technical point, in order to maintain the same magnitude in our predictions, since we're going to have less values in this kind of matrix vector multiplication, we normalize by a factor of 1 over p. And what this does is effectively aligns the expectation or expected values during training and testing. Because in testing, we'll put back all of the neurons. We won't be dropping neurons in order to make a deterministic prediction. And we want those to be the same magnitude or the same relative size. So as an example, if we have a dropout rate of 0.25, we first sample 3 Bernoullis in this case. If we want to apply dropout to the first hidden layer here. And in this case, it turned out that we got 1 for the top neuron, 0, and 0. So the way that we implement this is that we ignore the dropped value. We can just multiply it by 0, so it won't be used in the matrix multiplication. And then we rescale by 1 over 0.75, both the second and third neurons which have been kept. Similarly, if we've dropped 2, say the bottom one as well, we just drop that by 0. And we still use the same weight normalization because we're really just looking for the expectation to be the same. We don't rescale this further just because we've dropped more neurons. And in particular, if it just so happens that no nodes have been dropped, then we rescale everything, again, just to align the expected value, at least during training. So in training, they're rescaled, but during testing, we keep all of them by construction and do not rescale them. So just an implementation note, you have to rescale during training, but you do not after you're done training or during testing. And this is implemented for us already in TensorFlow. Another pseudo-regularization technique, which has gained a lot of attention recently, is batch normalization. So this can act in some form as a regularization. And the idea behind batch normalization is that we have a shift in what the network layers are seeing as their inputs as we train. So if I go back to the slide with 2 hidden layers, and I think about the inputs that the second layer is receiving, it depends on the values of the weights for this first layer as well. So at the start of training, it may have been seeing a lot of positive values here for the data set. But maybe during the optimization procedure, these weights have changed and switched so that now they're seeing negative values. And that can continue to happen. This change in the first layer can result in a change to what's going into the second layer. And this leads to an inefficient training process. So we would like to somehow standardize the values which are being seen by layers later in the training process. The idea of batch normalization is to do this by providing something of a normalization before each activation, but doing so in a way which is compatible with gradient-based optimization. So a lot of the optimization algorithms, or most of them, are reliant on gradients being computable. So we need to take this mean, but we also have to make sure that that mean and that rescaling are differentiable. So the proposed solution of batch normalization is to define the mean and a variance for each individual batch. So if we remember, we take a collection of examples, maybe 100 examples at a time. So instead of taking the mean for the whole data set, we'll just look at the mean for that batch, that current batch, before the layer. And we rescale and center those values by the batch mean and the batch variance. Okay, so we have the new x values, or the centered and rescaled values, are defined by centering and then rescaling with a tolerance term to avoid overflow. So in addition to this, so once we've centered these values, we may not necessarily want the values to be centered around 0. And we may kind of imagine that just having them shifted or rescaled to a standard deviation of 1 may not be ideal. So what we can do after that is apply a linear transformation to these normalized values, which is learned for each layer. So that layer may learn that it does want positive values, and it can do that by taking a positive gamma and a positive beta, for instance. Okay, and so it can encourage the distribution to be in a specific location, irrespective of what types of values were coming in. So x can take anything, it can change throughout learning, but the layer has control to some degree of where the distribution of inputs values will land. So just as in the case of dropout, we need to have a strategy for predicting or testing with this. And in particular, we don't want our testing or prediction method to depend on the specific data that we're using. For example, we don't want to take a batch mean and a batch variance anymore. Instead, what we can do is compute a global mean and a global variance, mu and sigma squared, for each layer, and shift that input according to those global mu's and sigma squareds. And although we could approach this directly by just applying our network and computing all of the mu's and sigma squareds on the entire training set after training, for instance, it's usually more feasible to take a running average, or a moving average rather, during training. So we can actually get this for free to some extent by computing a moving average of the mean and the variance for each layer. So it's not that we have to go and add an additional computation at the end. OK, so those are some of the techniques for regularizing the network. But we still haven't mentioned how we actually train or quantify the performance of a network. So yes, question?
So when during testing, when you are calculating the mean and variance on your own, how are you feeding that into the Bayes normalization data?
So when we're calculating the mean and the variance?
Testing,
Mm-hmm.
you are saying that we no longer need to calculate the mean and variance of every batch. So basically, we can calculate the mean and variance of the training set and feed it to the Bayes normalization layer?
Yes. So when we're in testing, we don't want to compute well, for instance, we may just be making a prediction on one value. So we don't want to take a mean of just that value and a standard deviation of that value, so to speak. Instead, we want it to be defined in terms of the training set that we've used. So what we can do is, throughout our training process, to keep track of these mu's and these sigma squareds, and define what's referred to as a moving average, or an exponential moving average. And we'll go over this once we get to the optimization algorithms. But effectively, it keeps track of the most recent values that it's seen. So to say the last 100 steps, the mean has been around 100 and the variance has been around 10, for instance. It keeps track of that with a way of ignoring some of the earlier steps. So we can use that as an estimate and then shift and rescale during testing using those computed global means and variances. So they're stored during training, or approximated during training, and then kept in the model, saved as a variable in the TensorFlow model, going back to that, to rescale any arbitrary input.
So you don't have to feed it separately during testing?
No, it will be stored in TensorFlow, for instance. It will be stored, and it will know to retrieve that when you say training equals false. So it's saved as a variable within the batch normalization layer. Yeah, no problem. And also, I should remind everyone that there is that technical detail when you're using TensorFlow and you use tf.layers.batch normalization, you need to include the update ops and use the line with control dependencies. So from my previous slides, so it's basically implemented for us, but there is that technical detail in the optimizer. We have to add one additional step. So just something to note. It won't perform this, for instance, if we don't do that. And I believe that's related to computing this exponential moving average. OK, so we want to now move to quantifying or evaluating our network's performance. And as we mentioned in yesterday's talk, the basic idea behind that is to define a loss. So we want to minimize some loss function. And in supervised training, which is what I'll basically restrict our attention to here, we have true outputs that we're working with. And typically, the loss function is defined as a measure of how close our predictions are to those true outputs. In addition to this kind of primary loss term, we can also have some auxiliary terms, such as the weight regularization. So maybe add to that loss the norm of the weights, so some weighted average of those network parameters, which are designed to help guide the training process. for example, to avoid overfitting in the case of weight regularization. So in two of the most basic types of neural network applications, we have something of a standard list of loss functions. So for regression problems, things where we're aiming to predict real values like 1.2, 10.5, or some kind of precise value, we typically use something like a mean squared error. There are other options, obviously, as well, but it's a very kind of simple function. We just take the sum of the squares, and then we take the average. And this average is important, as we'll see in the optimization section, but for the most part, we're just quantifying how far away each element of our prediction is from each element of the true solution. And for classification, we have two kind of default loss functions. So classification is the idea of assigning maybe a label or a class to a given input. And those two loss functions are the softmax cross entropy, which is used for mutually exclusive problems. So for instance, if we want to classify a digit, it's either a 0, a 1, or 2, et cetera, but it can't be both a 1 and a 3, for instance. So the softmax will be defined in a way that basically chooses one or is intended to choose one class or label. There's also the sigmoid cross entropy, which can be used in the case where it's not mutually exclusive. For instance, if we want to determine which objects are in an image, and there may be multiple. There may be a pencil and a piece of paper and other objects as well, so they may all be there, and in that case, we would use sigmoid cross entropy for the non-mutual exclusive case. One other note which is important when we're defining the loss function and looking to quantify the network is to make sure that we're feeding in the data in a way that the network can understand or appropriately distinguish. So for instance, if we're looking to predict a label for numbers like 0, 1, and 2, it's not a good idea to just give the network a single scalar value, 0.0, 1.0, 2.0. If we do that, it's difficult for the network to decide what the difference is between a 0 and a 1. If the value is 1 and it selects 0, it's going to, in some sense, think that it was close, because 0 is close to 1. But in reality, these are completely separate labels. We want to basically completely separate these values. And a convenient way which works in practice is to use what's referred to as a one-hot encoding. And the way that this works is that we simply make a vector with the length of the number of classes or labels that we have. So for instance, 10 in the case of digits. And we assign a vector with one value equal to 1, and the remaining values or entries equal to 0, corresponding to the position of that label. So in this case, the first entry being 1 corresponds to the label 0. The second entry being 1 corresponds to the label 1, et cetera. And so in this setting, there's a clear difference from the computer's point of view between the 0 label and the 1 label. They're not somehow closer than the 0 and the 2. And this is also very common if you want to look into word prediction. So you may have a dictionary of terms. So this would be a very large vector, presumably. And each word would be assigned a specific location. And also for character level predictions by defining like a character set. So maybe all the letters, maybe capital letters, and it will depend on the specific application. But for discrete types of data, this is often a more effective way to implement your network. In addition to that, we typically are recommended to use some sort of normalization on our input data. And this is basically just mimicking what batch normalization did in batches. But if it's feasible, it can be helpful to just normalize before you train, before you even start defining your network, to just normalize by centering and rescaling your data. And this should be a plus sign, I apologize. So that should be a plus. And once we do this, we have some inputs which the network can basically identify as large or small, Whereas if we don't perform this normalization, it may be difficult. For instance, if you consider maybe you have data which is centered around 100, and all the values lie roughly within the interval 99.9 and 100.1. Well, it's difficult in this neural network setting to really distinguish between 99 and 101 or 99.9 and 100.1. Right? We're just going to do some matrix multiplication. It's not going to be able to switch or make a decision based on the fact that 99.9 just so happens to be very low in this data set. It's a very extreme case, and 100.1 is a very extreme case on the opposite end, whereas the rescaled values will reflect that. So it's just another thing to keep in mind as you're designing your network, and if it's not performing well, it may be something like this could be of benefit. Okay, so we've defined the loss, but we still need to figure out how we're actually going to use that loss information to tune or adjust our network's parameters. And the basic idea comes from just kind of your first year of calculus, the idea of gradient descent. So we'll just take the loss function f, we'll take its gradient, add a negative sign in front of it to go in the direction of steepest descent, and then make a move of some specified step size in that direction. Okay, so we'll just somewhat walk our way down this manifold and hopefully find some fixed point where the values have converged to a local minimum of our loss function. And so this convergence is guaranteed under certain convexity and continuity assumptions. They're usually hard to check in practice, but in reality, it often works. But we do have to be cautious about things like local minima and situations where we have saddle points tend to give us difficulties. But the basic idea is just to follow this descent scheme. The problem with this that comes up right away, though, is that our loss function is actually quite complicated in the situation of training neural networks. Okay, so we can kind of rephrase that previous scheme in terms of neural networks by interpreting our parameters as the values that we're looking to adjust or tune. So our parameters are in some parameter space. We have some initial guess at those parameters, and we want to find the ideal parameters, theta star. Well, to do that, what we're actually trying to minimize is a loss on the entire data set. So our loss function will be defined in terms of those parameters, theta. So if we fix those parameters in some position, what is the average loss over all of the examples in our data set? So this loss, like the mean squared error or the sigmoid cross entropy, for example, will be computed for every training example. And in particular, we'll need to compute the prediction, the network's prediction for every one of these examples. So if you have a data set with hundreds of thousands or millions of examples, this is not realistic. This is very hard to compute, and this is required by the standard gradient descent at every step of the optimization procedure. Okay, so this is simply not going to work in the context of neural networks. Instead, what we can do is approximate that gradient. So we need the gradient to provide us a direction of steepest descent so that we can optimize our network parameters. Instead of computing it on the entire data set, we may think to use the batch idea again. Okay, so similar to batch normalization, why not at least approximate the value of the gradient so we have some idea where we're going. This will be a stochastic approximation because it will depend on the samples that we're working with in that current batch. But if the noise level is low enough, we still should be able to somewhat random walk our way to a local minimum. That's the idea. And the way that we do this is we just define the same average, but scaled by the size of the batch instead to maintain the same relative magnitude. And we define the update step the same as before, just using this approximation of the gradient rather than the gradient on the full data set. So this works well to address the first problem that we mentioned. We really can't compute that actual loss function, at least not on every step of the optimization procedure, but there still are some potential obstacles in this approach. So one obstacle that comes up is that the fixed learning rate is usually not optimal. It's usually better to adapt the learning rate and react to different situations that you find yourself in. For example, if you're leveling off, you may want to slow the learning rate down so that you can get a more precise prediction of that local minimum. In addition, it's difficult to find that fixed learning rate if you are using a fixed learning rate, or even a starting learning rate, because it really depends on the problem and the scale of the problem that you're working with. In addition, and perhaps more important, it's usually the case that different parameters will require different learning rates. Okay, the gradients may be different orders of magnitude and different parameters for different parameters, and we want our learning rate to be reflective of this. So we want to learn at different rates for different parameters if that results in better performance. And also, since the directions and the magnitudes of the previous updates are never taken into consideration in this standard batch stochastic gradient descent, we can really lead to a very noisy and inefficient training process. We may end up going to the right and then to the left and to the right, to the left, and kind of bouncing all over the place instead of kind of carrying on in the direction where the parameters are actually meant to go. And so just to demonstrate kind of again in this cartoonish diagram, the importance of learning rate, we can imagine having a learning rate which is too high or a learning rate in which is too low. And on the left, we see that when it's too high, we may get near a local minimum. But after we get close, our learning rate is high enough that we actually repeatedly skip over the true minimum. And in the extreme case, it may never actually converge. It may just keep going back and forth, and it will never actually find that precise minimum there. Okay, and so this is, again, a situation where we may want to have an adaptive learning rate which begins to understand that it should slow down and work on zeroing in on that minimum. In the other extreme, a slow learning rate would result in a extremely long training process. So this will, in theory, get to the minimum, but it may take weeks or months, whereas a slightly higher training or learning rate may get there in a matter of hours. Okay, so we may just slowly work our way down, but in this case, it's not the ideal setting, and we've just kind of chosen this, and so we want to get around these issues. Okay. And so there's a number of concepts that have been introduced to work with this, the first of which is Nesterov momentum. And this was introduced more than 30 years ago and addresses the idea of that back and forth. If our learning is going to the left and then to the right, we want to get some sort of momentum to inform the network that it was moving in this direction, it has been moving in this direction, and that it should keep moving in this direction for the most part. We want to somewhat limit the noise from kind of outlying batches that come up in the training process. And the way to do this is to define a sense of momentum, which starts out at 0 and then is defined recursively in terms of the previous momentum and the current estimate of the gradient. So once we define this, we take that momentum into consideration and apply our update step. So this is exactly as before if we just had this term, but we're adding this additional term corresponding to the momentum, which has an influence to keep it going in the same direction. And this is the standard momentum, and then the accelerated version, introduced, by Nesterov, takes advantage of the fact that we can actually look ahead using the calculation of momentum from the previous step, where we would end up if we were to follow that instruction, take the gradient there, and see how that aligns with the current momentum. So this is kind of a looking ahead scheme. We see, if we're going to change directions, maybe we'll slow down and help zero in on the local minimum. And so I'll just go briefly over some of the the methods that have been introduced recently, around like 2011, there was AdaGrad, RMSProp, and then AdaDelta. So AdaGrad was the first of these papers, and it looked to normalize the gradients by the sum of the squares of previous gradients. And so this had a natural decay in learning rate, which was helpful and worked in a lot of problems. But often, since it was summing up the squares of all of the previous gradients, it led to this decay which was too fast, and learning terminated before the minimum was actually reached. So RMSProp and AdaDelta both offered corrections to this around the same time, and in particular, RMSProp kept a moving average instead of just summing the squares of the previous gradients, and used that to rescale updates. And AdaDelta had an alternate rescaling, and many, many other variants exist. For example, adding momentum to those two methods. One common theme, and that we've already mentioned earlier, to these methods is that of an exponential moving average. And the exponential moving average, as I briefly mentioned, is basically a way to keep track of the global or the universal average or value of some quantity, but to have a preference for the most recent values. So for example, if your distribution is actually changing, as is the case with neural networks, we want to track that mean, and that mean may be moving. So we want to keep track of the most recent values, but we still want to have this sense of an average from values further back. And the way we can do this is just kind of this clever recursive definition. We define an exponential decay rate less than 1 beta, and we define the current value as the previous value, a weighted or kind of an interpolation between the previous value and the current prediction. So g of t, in this case, corresponds to the gradient calculation at the previous value, and we take this kind of weighted sum of the previous and the current. And what happens if we unpack this is that we get a sum, basically, of these previous values, but it's weighted by this parameter beta raised to a power which increases the further we go back. So if we go back to the start, it will have something like beta to 1,000, and that will be very, very low in terms of its impact on the final mean. So this is used in the atom optimization algorithm, which I want to go over. The atom optimization algorithm is one of the more efficient and widely applicable algorithms, also available in TensorFlow. And the basic idea behind atom is to keep a moving average for both the first moment and the second uncentered moment, which really are just the gradient calculation, g sub t, and the square of that gradient calculation, so g sub t squared. And one technical point that they made in this paper, which is of theoretical importance, is that initializing these moving averages at 0 actually leads to a biased estimate. So there's no reason that it should be 0, and we can actually get rid of that bias or remove that bias through kind of a simple rescaling given here. And if you consult the paper, they give the full probability theoretic justification for how this creates an unbiased estimate. So I'll leave this for you to review in the slides, but the implementation of the atom optimization algorithm is quite simple. We just compute the moments, create unbiased estimates, and then rescale by those unbiased estimates. So it's quite simple, but has a number of interesting features and actually helps to converge more quickly and more accurately to the local minimum. I would like to resume, and I wanted to stop before we got to this because this is, in fact, the kind of core of how neural networks are actually trained. In particular, I want to discuss the concepts of backpropagation and automatic differentiation. I think these are two very interesting concepts, and they're definitely crucial to the actual implementation of neural networks on computers. So the notion of backpropagation was introduced in a fairly easy-to-read article in Nature in 1986, and I'd encourage you to consult it. Somewhat of a kind of a seminal work. And this goes about addressing one question that I've left unasked in the earlier parts of the presentation, which is how are the gradients actually computed? So we know in theory that we're going to compute this gradient of the loss function, and we know that once we have that gradient, we can tune our hyperparameter, or our model parameters rather, but we still need to actually compute that gradient. And we need to do this in a kind of efficient, scalable way. So one approach to handling or addressing this problem, known as backpropagation, as I mentioned, is to basically propagate back errors one layer at a time, or one network parameter at a time. And I'll go back to the notation used in this paper, because as I mentioned, I think it's nice to refer to. And the way that they defined their loss was referred to as an error, and it was 1/2 of the sum of the squared error for the predictions. And so the way that the paper is written, its notation is a little bit kind of confusing at first, at least it was for me. But the way that they have it set up is they imagine an input or a kind of first layer, which is labeled by I. Okay, so I prime, I double prime, et cetera. And there are inputs x to that layer, like prior to the activation, for instance, and outputs y after the activation, the actual result of that node. And those values are, those y values are multiplied by the weighted sums added together with a bias to produce the next input to the second layer, which are labeled by j. So just a notational, the notation behind the paper is there's an I layer and a j layer. And this is basically the layout of the original paper. So based on the error function, or the loss function that they've defined, we can easily compute. We already know what the derivative of the error is with respect to that last output. It's just yj minus dj. And in particular, if we have some more complicated loss function, we can always compute that. That's not difficult to compute the derivative of a function with respect to one of its direct inputs. What we want to figure out, though, is how does the xj influence that error? What is the derivative of the error with respect to xj? And the reason we want to know that is because eventually we want to know what the error is for the weights, because that's what we're trying to optimize. So once we have computed the error for yj, we can actually apply just a fairly straightforward use of the chain rule to compute the derivative with respect to xj as the product of what we already know, what we've already computed, and the derivative of yj with respect to xj. But the value of yj is just kind of a straightforward, it is defined in kind of a straightforward manner in terms of xj. It's just the activation function, sigma in this case. It was a sigmoid, but this works equally well for any activation function that we can compute the derivative of. And we can directly evaluate this. We know what xj is. We know what the sigmoid function is, or our activation function is, so we can compute its derivative and multiply that by the value that we've just computed in the previous step. And now we can imagine taking a step further back to the weight matrix. And again, we can play this same game using the calculation of our previous step along with the chain rule, and noticing that the value of xj, which is defined linearly in terms of these weights and the y values, is just going to be, so this derivative is just given by yi in this case. So it's just the value of this input if we take the derivative with respect to this weight wji. Okay, so we can also compute this because in the previous step we just identified the value or computed the value of the derivative of the error with respect to xj. And so lastly, we can go one step further. We look at yi, and this will have multiple kind of paths, so to speak, to influence the outputs, or will affect multiple outputs. But really, we can just add those up. And so we'll apply the chain rule and sum the influence it has on each of the outputs. And again, just the chain rule, and noticing that xj depends linearly on yi. So xj depends linearly on yi. According to that weight, we get an expression which we can compute, because we know all of these from basically the first step of our algorithm, and we know all the weights. And now once we've got back here, we can just repeat the process, because now I know all these yi's, yi prime, etc., and that's exactly the position that we started in. Okay, so now we've computed, in particular, the derivative of the loss with respect to the previous layer. So if we want to go one layer back, then we just repeat this step. And this allows us to define networks with many hidden layers and simply propagate back the error in this fashion. So the back propagation, the name is derived from the idea of starting at the end and going backwards slowly to compute each of these values. And we can do this indefinitely. Now, this gives us kind of a plan for computing the derivatives, but it still hasn't actually given us the way that we would compute these derivatives for our network functions. And two common approaches are symbolic and numeric differentiation. And these are both kind of used widely, but not applicable, at least not kind of applicable in the sense of an efficient implementation to neural networks. So symbolic differentiation leads to exact derivatives by acting on the expressions which define functions. So you can think of things like sine of x and having in something like Mathematica a kind of knowledge that the derivative of the symbol sine of x is cosine of x, for instance. And you can define a number of these and build up a library of derivatives which you can compute exactly. The problem with this in terms of efficiency is that those expressions that you obtain may not be the most efficient implementation of evaluating the derivative. So for instance, you may have a significant number of cancellation in your expression. Maybe the derivative comes out to be cosine of x plus 1 minus cosine of x. Well, you really just need to evaluate 1. The computer doesn't need to do much at all for that. But in the symbolic computation, as it stands, it would have to compute cosine twice. Now, you can simplify this, but the simplification is even more inefficient than just running the original inefficient implementation. So this is really not going to scale well as we add more and more layers and have to compute more and more derivatives. The benefit is that it gives exact computations of these gradients. The second approach that we have available is numeric differentiation. So this is widely applicable. We can basically do this on any type of function, even functions defined in loops, in more complicated ways. So its applicability is nice, but the problem is that it does not give us the exact gradients that we're looking for. And in particular, if you define a network with millions of layers and millions of parameters, which is commonplace nowadays, these small errors in each gradient calculation combine to form a completely unstable training process. So it's just not acceptable to have these inexact gradients. So what this leaves us with is a situation where we need exact gradients, but we need to be able to compute them efficiently. And the solution, or the method of achieving this, is referred to as automatic differentiation. And in one embodiment, this is a generalization of backpropagation, or the kind of underlying idea behind backpropagation. And so what TensorFlow uses in particular is referred to as reverse mode automatic differentiation. And the reverse mode kind of refers to that idea of backpropagation. I would strongly encourage people to refer, if they're interested, to this work by Biden, Perlmutter, Rottle, and Siskind, or to these lecture slides for kind of a briefer analysis. But the basic idea behind the notion of automatic differentiation is that it's going to compute the derivatives by taking advantage of the existence of a computational graph. Okay, so we have this graph outlining the computations that we are making along the way, so to get from input to output. And so what we can do is keep track of those operations and at a code level, not a symbol level, but on the code level, keep track of a tape, which is referred to as a Wengert list of those operations, and the associated operations for computing the derivatives. Okay, so what this does is it leads to an efficient code-based implementation of calculating derivatives, which is very fast in terms of evaluation time and only has basically the one disadvantage of requiring a little more memory, but that's usually not our main concern. We really want to be able to compute these quickly, so the reverse mode will give us a quick evaluation time at the price of a little bit more memory. So that's all I have for automatic differentiation, and if you're interested, again, I would encourage you to go to those slides.